So, we continue with the problem set. The next problem, okay, so we for problem 3 we just did the first part and we found out that for a geostationary orbit the orbital average height of a geostationary orbit from Earth's surface is approximately, or I should say average height we found out is 6.6 RO. So, the situation is following. So, we have so this is our Earth with a radius r0, okay, and a geostationary orbit is a geostationary satellite is a satellite which stays, let us say, on this particular point on Earth, and it rotates along okay. So, it rotates along with the Earth. So, T s, which is the time period of revolution, is 1 day, that is 24 hours. Okay. And we have seen that the average radius which is given by this length a, which is from the measured from the force center, is approximately. So, a we have found out that approximately 6.6 RO, right. Now, if this is 6.6 RO and this is RO, then the actual answer to problem question 3 problem 1, what is the average height of a geostationary orbit from Earth's surface? So, the answer will be h, which will be equal to a minus r0 is approximately 5.6 RO, right. So, this is the answer. Now, move to problem 2. Problem 2 is for a satellite, the maximum and minimum distance of a satellite from Earth's surface is given. Find out the period taking, okay, so I should get, yeah, so I have taken r equal to 3678, which is more accurate number, but so far we have taken 36400, which is also okay, it is not very bad approximation. Oh, okay, sorry. So, this second part should not be here, okay, it's my mistake, okay. This part should not be here, so please ignore this. So, we are interested only up to this, and then we have to find out what is the eccentricity of this orbit. So, question number 2 is if the maximum and minimum distance of a satellite is given, and we have to find out the time period. Okay. So, let us do that. So, if we come back to this and let us start with this picture once again. Okay. Now, for a satellite, okay, so this was a different picture, let us draw a fresh diagram, let us start over. So, once again this is my Earth surface, there is a satellite and we know that in general the satellite path is an ellipse. Okay. So, let us say this is the abyss line for that ellipse. So, it goes something like this. Sorry, my drawings are not very nice, I know that, I try to improve on that, but not working that well. Okay. So, this is the point of evolution. So, this is my force center. Now, this is my apogee distance, this is my perigee distance, right. These two distances are given. So, 1000 and 2000 kilometers respectively from surface. So, we have a radius r0 and this one is given as 2000 kilometer and this one is given as 1000 kilometers, right. So, R A is equal to H plus H max plus R 0, R P is equal to H min plus R 0, H max is equal to 2000 kilometer, H min is equal to 1000 kilometers. So, once we put all this, 2a, which is a distance from this to this, will be 2r0 plus 1000 plus 2000. So, essentially 2r0 plus h min plus h max. So, which gives you an a, which is, if you go by this exact calculation, so your a will be 15800. We actually, okay, let us use r0 equal to 6400 only. Don't use the value of 6378. I mean, you can do that, but let us use this, because we are through and through we are using 6400 kilometers, right. So, once we get these, and so what we need to find out is the time period of the satellite. Now, once again, from Kepler's third law, we know that the time period is time period square is equal to the average radius cube. So, average radius in this case is the length of the semi major axis we have to take. Okay. So, this is a standard norm. There are two lengths, one is the length of semi major axis or major axis, one is the length of minor axis, but typically in Kepler's law it has been found out that the length of major axis is what we need to take into account, semi major axis. So, Ts is equal to As by Am whole to the power 3/2 times Tm, right. So, we put As, so what is Am and Tm? Am is the average distance from Earth to Moon, and Tm is the time period of the Moon. Why it is important? Because Moon is also a satellite, it is a natural satellite, but it is a satellite of Earth which is orbiting Earth in a much higher orbit somewhere there out, I mean at a long distance from Earth's surface. But according to Kepler's law, it does not matter if it is close by or if it is very far from the Earth's surface force center. If it is a satellite or if it is something which is evolving around a particular force center, it has to follow Kepler's law. So, Moon is something that can be taken as a reference. Okay. So, we know that from this problem that Tm is equal to 27.3 days and Am is equal to 384,000 kilometers. So, we have to put these values back here, and if we do that, we get so 79. Oh, sorry, this is 2a equal to this. So, a will be equal to 7900 kilometers. Okay. So, a is equal to this, or As is equal to this, right. So, 7900 by 384,000 whole to the power 3 by 2 into Tm is 27.3 days. So, from this we get Ts equal to 0.0805 days. Now, if we want to express this in terms of the numbers or some hour, minute, second, then we can get Ts will be equal to, it will be something approximately 1 hour 55 minutes and 48 seconds. So, this is an approximate number, but very pretty accurate. So, this is the time period of evaluation of this particular satellite. So, this time period of evolution is determined by a direct use of Kepler's laws of planetary motion. That is the third law. Good. Now, the second or last part of this problem, we have to find out the eccentricity of the orbit. Now, for the eccentricity expression, please remember that R A, that is the apogee distance, is given by L into 1 minus epsilon, R P is given in as 1 by 1 L by 1 plus epsilon. Okay. So, from this we see that R P P by R A is equal to 1 minus epsilon by 1 plus epsilon. Okay. So, if we do some simplification here, is it right? Yeah, yeah. So, if we do simplification, we will see epsilon is given by R A minus R P by R A plus R P. And also, if you recall, R A is the distance which is farthest from the force center and R P is the distance which is closest from the force center, right. So, if this is the case, if you recall, we have a velocity v min in the farthest point and a velocity or speed v max in the closest point, and if we can also write eccentricity is equal to v max minus v min by v max plus v min. We did that in the class. Okay. So, right now we will be using this equation. Okay. So, epsilon will be equal to so R A is what? R A is 2000 plus R 0 minus R 0 minus 1000, or rather minus R 0 plus 1000 divided by R A plus R P is nothing but 2 A, which we have already calculated. Here R 0 cancels. So, it is 1000 divided by 15800, which is approximately equal to 0.0633. So, we see that eccentricity is small. So, the orbit is not very much like an ellipse, I would say. It is pretty much close to a circular orbit. Anyway, so this is done. Now, we move to the next problem, or actually in the same line we can finish problem number 5 at first, and then we can move to problem number 4, right. Now, in problem number 5, what is given? In 5, it is given that the Sputnik, which is a Russian satellite, Sputnik 1, which is the first of the Russian satellites in outer space, it has a perigee of 227 kilometers above Earth's surface, with a speed of V max is equal to 28,710 kilometers per hour, and we have to find the apogee distance, the speed at apogee, and period of evolution, right. Now, how to approach this problem? So, what is essentially given is, if we go back to this particular picture, let us say. So, let us say this is the orbit we are discussing. The perigee distance is given, which is the point of closest approach to Earth, which is at 227 kilometers, and V max is given. Now, at first this might look very, the problem where proper information is not given, because at first you might think that okay, this is not sufficient information to calculate this. So, what we need to calculate is the apogee distance, which is R A, speed at apogee, and period of evolution. Okay. So, what is given is V max is equal to 710 kilometers per second. And R P, which is the perigee distance, is 227 plus 6400 kilometers, which is 7266 kilometers, right. So, these are the only two informations we have. Now, how can we use this information to calculate the speed at apogee, the apogee distance, period of evolution, things like that? How is it possible? It is possible because if you now come back here and look into it, we have this particular expression. So, if we can somehow get the value of eccentricity epsilon, from there we can, so we already know V max. So, if we know epsilon, we can immediately calculate V min, and once we know V min, calculation of R min. So, R A is not very difficult. So, what we need to calculate is V min and R A. Period of evolution is pretty straightforward afterwards. Now, how can we do that? Please recall that now let us look at this situation. The distance we know, this is the perigee distance. For this particular case, the perigee distance we just calculated is 6,627 kilometers, and V max is given, right. So, we can calculate the L, angular momentum, from this information, because at perigee the angle is 90 degree. What is the expression of L at this perigee? Is m r which is R p into V max, right. So, this is the information we have in hand. Now, with if we put values, of course, we do not know m, which is not terribly important. And of course, there is a sin alpha which will be alpha equal to pi by 2. So, sin alpha will be equal to 1, right. Now, C is given by V by V e, which is 28710 divided by the escape velocity. Now, this is something, please remember, I told you previously that escape velocity, what we know is the escape velocity from Earth's surface. Okay. So, escape velocity from Earth's surface is something we all know. For this particular case, the satellite, when it is at its perigee position, it is 227 kilometers above the Earth's surface. So, definitely the escape velocity, which the value of escape velocity will be changing. So, first of all, for this problem we need to calculate the value of escape velocity from this height, for this particular height. Now, what is the expression for escape velocity? The escape velocity expression is root over g, sorry, there is a 2 here, 2 g m by r for a distance r. Now, what we can do is, once again we can put the values of gravitational constant, mass of earth, but which is not terribly needed. It is not important to know all these values. What we can do is, we can simply write this in this particular form into root over r 0 by r, right. And this we already know, it is 11.2 kilometers per second. Now, we just have to multiply this with r 0 divided by r 0 plus r p. So, V e is equal to 11.2 into root over r 0 is 6400 divided by, it is 6627 kilometer per second. Now, if we do that, we will get a number which is, okay. So, I do not have this calculated, but we can do that. It is not so difficult. Okay. So, it is 6400 divided by 6627, okay, whole square root multiplied by 11.2. Okay. So, it will be 11.006 kilometer per second, or we can approximately take it as 11. Okay. Now, so V c, which is given by V by V e, will be 28710 divided by, okay, this is kilometer per second. Now, if we have to change it to kilometer per hour, which is the speed given, which is the unit of the speed given for the satellite. So, please remember this V is 27 kilometers per hour. So, we just have to multiply this 11 point something star 3600. Okay. So, it is 39,623 approximately 0.4, right. So, if we do this, perform this calculation, it will be 28710. So, it will be approximately 0.72. 7245, we will just call it approximately 0.725. Okay, all these approximations will introduce some error into the calculation, but it is okay because we are not, anyway we are not doing it very accurately. Now, epsilon equal to 1 plus or 1 minus 4 c square 1 minus c square sin square alpha, right. So, again sin alpha will be equal to 1. So, in this particular case it will be 1 minus 4 c square, c is equal to this. So, c square will be 0.525 into 0.525, okay, into 1 minus c square is just this minus 1 into 0.475, okay, 475. So, if we execute this star 0.525, okay, into 4 and plus 1, okay, and if we take root of this, so eccentricity epsilon is approximately equal to 0.05, yeah, approximately 0.05. Okay, so you can always, I think it's okay. Okay, you can do this calculation by yourself and check the number, but what is important that in this way, just by knowing the speed at perigee or speed at one of the apicidal points and the velocity, the distance of that particular apicidal point, it is sufficient information to get to the eccentricity of the orbit. That is all we need. Okay. And also please remember that in this type of calculation, we have to recalculate the escape velocity in this manner. Now, once we do that, and now we are in a position to put the values in this particular expression. Okay. So, once for the apogee, so in this case if we use this particular expression, then we can calculate the apogee distance, and if we use this particular expression, then we can calculate the minimum value, right, or minimum value of the velocity. So, I am not doing it, you can finish it yourself, that is not a problem, but once you get eccentricity and you have these two expressions in hand, it is really easy. Okay. Fine. And for the third part, period of evolution, once you have for this last part, once you have the apogee distance and the perigee distance, and if you add them up together, then you will get two times a. From there you can calculate the length of semi minor axis or semi major axis, and immediately that is useful for calculating the time period, because we know that we can use this information that moon has a time period of 27.3 days and the earth to moon distance is this, right. So, I am leaving it on to you to finish this problem, the numerical calculation, but it will be easy. Now, let us come to problem number 4. This is the last problem of this problem set. What is given is V is equal to V e by root 2 and alpha is equal to pi by 6, right. So, see it is, and we will see that this will lead to a ballistic missile case. So, we will treat this as a projectile. So, we see c is equal to 1 by root 2, okay, and epsilon, if we put the value as 1 4 c square 1 minus c square sin square alpha, as c is equal to 1 by root 2, this whole thing will reduce to root over 1 minus sin square alpha, which is nothing but cos alpha, right, Of course, it will be plus minus, but epsilon cannot be negative. So, we have to say epsilon is equal to cos alpha. So, this is the first part, right. Now, what we need to calculate here is how high does the projectile rise and what will be its range. Now, there are two parts. Okay, so immediately we have already calculated that epsilon, the value of epsilon. Now, we have to calculate how high does the projectile rise. Okay. This is given by the apogee distance, which is L by 1 minus epsilon. Now, L is L square by m k, and just like we did during one of our previous classes, so we have to substitute for L and m k, L and k. Once we do that, L will be m square v square r 0 square sin square alpha m, and k can be replaced by m v e square r 0 by 2. We put r 0 because here the projectile is fired from the surface of the earth. So, once we do these cancellations, we are left with r 0 sin square alpha. So, r a, which is this, is r 0 sin square alpha divided by 1 minus cos alpha, and you can please see that r 0 sin square alpha can be written as r 0 1 minus cos square alpha 1 minus cos alpha, which will be r 0 1 minus cos alpha, right. So, the maximum height which is achievable is r 0 1 minus cos alpha. So, if we put the value of alpha equal to pi by 6 in this expression, then it will be something like 1.866 r 0. So, this is the maximum height at which this ballistic missile will rise. And for the range, we have to find out phi 0, because please remember, range is given by range r is given by 2 phi 0 r 0. Okay. So, we have to calculate phi 0. Now, there was this expression for phi 0, which is cos phi 0 is equal to 1 minus 2 c square sin square alpha into root over 1 minus 4 c square 1 minus c square, which is the expression for epsilon. So, we should not write this, because this is nothing but root over epsilon. Okay. So, what we can do is we can simply write this as okay. So, the numerator stays like this. For denominator, we can just substitute it by cos alpha, okay. And again c is equal to 1 over root 2. So, c square is half. So, it will be 1 minus sin square alpha by cos alpha. Okay. Now, 1 minus sin square alpha is cos square alpha. So, this is essentially cos alpha. So, we see that cos phi 0 is equal to cos alpha. So, alpha is equal to phi 0, right. So, the range, which is 2, so we put alpha equal to phi 0 or phi 0 equal to alpha 2 alpha r 0, which is 2 into pi by 6 into r 0. So, range r is equal to pi by 3 times r 0, right. So, this is the expression for range of the projectile. Of course, you can put values r 0 equal to 6400 kilometers, pi we know, and we can get a number for it. Okay. So, we concluded this discussion of central orbit with this problem. So, this was a problem set we discussed in today's class. Of course, we had one more problem set beforehand, which we have already discussed. So, one thing, okay, many things we could not cover during this discussion. For example, we could not cover scattering, we could not cover orbit transfer in details, and also I did not have time to go through the details of stability of the orbit. But anyway, these are some advanced topics which probably you will find out in your later courses on classical mechanics. Of course, things related to special and general theory of relativity can also be included in this discussion of central forces, which we could not do during this class. But whatever we have learned, I think this is enough for, I mean, this is good enough for you guys at present, and hopefully we will move on. I mean, hopefully we will continue our good learning experience in the next chapter, which will be motion in rotating coordinate systems. Thank you.